Okay, so good morning. Today, I'll be discussing our first lesson in numerical methods. Yeah. So this ebook uh, was done way back 2018. That means I started teaching this 2018. Although alam ko, 2017 pa lang, first time in TUP, nagturo na rin ako. No? I forgot po. No? And I used Text Studio in compiling this ebook. And it was posted already sa ating MS Team. Yan. Okay. Yan. So this is the contents. Take note po, yung contents nito ay just parang ano lang siya, no? Snapshot lang ng mga nakuha ko sa book ni Amos Gilat. The book ni Amos Gilat is actually this. Okay, this one. I have a hard copy of this. Okay, naiwan ko lang sa school, no? Yan po, no? Numerical methods for engineers and scientists using MATLAB. Okay, although my goal is uh, to customize the ebook, so nag-i-insert din ako ng mga personal spreadsheet ko, personal MATCAD file, MATLAB file, and ano nga yung gamit ko na isa? Math Studio na na freeware. Yan, okay. Basically, we have how many chapters? 8, no? 8 po yan, no? Okay. Number 1 is deals with vectors and matrices, no? Kramer's rule na we all know since college, and a very typical solution using Excel. Sometimes nasusurprise ako, baka hindi nyo rin pa alam, no? Actually, nung nag-masters din ako sa UP, that's the time I realized yung no, yung power ng Excel sa matrix analysis, no. So I believe it's wise to share this sa inyo rin, no. Yan. Next is differential equation, kasi of course lahat naman ng engineering phenomena, if not all, almost all phenomenon in engineering can be di ba, can be converted into a differential equation. And that's what we are solving, no, numerically, no, in this course, no, because may mga equation na it's hard to solve analytically. Yan. Okay, for example, yung problem ng finite element, no, it's actually a numerical methods problem, no, but since finite element is a wide subject, although part pa rin siya ng numerical methods, so it's wise na ihiwalay siya as a course. Okay. So I taught finite element then last sem, no, second sem. Tapos we will be talking also of functions of two or more independent variables. Yan, lalo na partial differential equation, di ba? Partial differential equation deals with, say, 2D plane, no? For example, pag one-dimensional lang kasi, one variable ka lang, linear lang yung 1D plane lang yung kino-consider natin. But if you're dealing with 2D plane or 3D, three-dimensional, partial differential equation na yon, no? Na pasok din ang finite element method. Okay. Tapos, in-insert ko ang Taylor series because you will notice most of the solution that we will have sa numerical methods will stem from Taylor series. Yan po. So next is the roots of equation. Yan. Actually, this is a non-linear solution, no, of differential equation, itong chapter 2. So we have here the bisection method, regular falsi method, and Newton's method, second method, the MOS or the method of successive substitution. Like this one, MOS, wala naman to kay Gilat, no? Pero in-insert ko siya. Tinuro sa amin to sa UP ni Sir Templo. Yan po. And of course, the use of MATLAB. Tapos equations with multiple roots. and system of nonlinear equations. Yan. So then next is chapter 3, solving system of linear equations. So I think itong system of linear equations parang majority ng software, no, lalo na sa amin structural engineers, ito yung may direct application eh, no? Kasi sa amin sa structural engineers, we're solving we are solving structures. Okay? So for example, yan. Okay. Say this is a structure. Yan. Okay. Yan po. So this structure has an inherent property we call K, or stiffness. That stiffness is a function of inertia. No? Eh, ano ba ang inertia? I equals bh cubed over 12. Yan. Okay. Tapos, when you solve this structure, we follow the stiffness method. No? Kaya nga stiffness yung kailangan natin. No? Which has the general formula of P equals KU. Yan. Wherein P is the force vector. Force vector means it's a column matrix. No? Yun po yung ano natin. Tinatawag ko na lang siyang vector. It's a force vector. Pero it's a column matrix. Kasi meron din tayong row vector. Yan. Okay. Next is the stiffness, the K. Yan. And the displacement. Yan. So, in this structure, given ang P, no, tayo ang nag-a-assign yan as engineer. No? Okay, given yan. No? And the stiffness will be given kasi minumodel mo yan. No? You assign the property, the cross-section of the building. So, given yan. Therefore, it's a one equation, one unknown problem. But, remember, we're dealing with matrix. Yan. And this is analogous to this equation. Ayan po. Wherein B is the force vector, A is the stiffness, X is the displacement. And how do you solve this? X, or the unknown coefficient, is equal to A inverse B. Yan. So, ganun din po dito, no? I-relate natin yan sa P equals KU. Therefore, the displacement is equal to K inverse P. Okay? Therefore, this is a very famous formula in system of linear equation. So, ibig sabihin, when you analyze building sa civil engineering, we're dealing with almost the same pattern of problem, no? System of linear equation. Yan po, no? But in a form of U equals K inverse P. Yan. So therefore, ibig sabihin, kinukuha namin yung inverse of the matrix. Yan. Of the stiffness. Then, imu-multiply sa force vector to get the displacement. Yan po. So, yun ang stiffness method, which is a direct application of solving system of linear equation. Okay. Pero syempre, pasok muna tayo dun sa elementary methods of solving system of linear equation, or say the old school approach, the Gauss elimination, no? Gauss elimination with pivoting, Gauss-Jordan elimination, LU decomposition. And ito nga, very uh, similar do sa ginawa ko, it's the inverse of it's the getting the inverse of the matrix. Yan. So using Excel function meanverse. Yun lang po 'yan. Which is madidiscuss ko din naman dito no, saglitan no. Madidiscuss ko din 'yan dito. But this topic we will go deeper no, kung ano yung mga other ways to invert matrix. No? Ito shortcut lang po to sa Excel, yung meanverse. And other method is Jacobi, Gauss-Seidel, tsaka tridiagonal, no, which is very important sa large matrices. Yan. Kasi hindi na efficient yung itong mga method na to nasa ibabaw pag malaki na yung matrix mo. Like sa building, no? Malalaki na yung matrix nun. Okay. And then of course, using MATLAB. Chapter 4, curve fitting. Yan. Alam naman po natin, no? Pag nag-experiment tayo, we have sets of data. No? Tapos, say, you have this a graph, no? Meron ka mga data sets, no? Pinopoint mo sila. Ayan. Tapos, you wanted to get the relationship, no? So, the idea is you curve fit. You fit a curve that will fit. You get the curve that will fit dun sa trending ng data natin. Parang ganun lang po, no? Okay? Halimbawa, alam naman natin sa engineering, no? How do we get the stress strain diagram of a steel? You test it by certain pressure, stress, then you get the strain. Get another stress, get another strain, get another stress, get another strain, until you come up with this kind of stress strain. Yan po, no? So, this is the Fy, the yield strength, and this is the nonlinear region of our stress strain diagram. Ayan. Okay. Now sa curve fitting, mas for another application, etong Lagrange polynomials, no, has an application sa finite element analysis. Ayan, no? Kasi sa finite element analysis, nag-a-assume tayo ng displacement. In our case, sa civil engineering, nag-a-assume kami ng displacement ng member. Say, halimbawa, beam. No? Say, this is a beam. We will assume a certain displacement function. No? Displacement curve of that. No? In the terms of function. Tapos, that basically is curve fitting. No? Then, using Lagrange polynomial. Kumbaga, you express this assumed displacement by Lagrange polynomial function. Basically, yun na po yung application sa amin nun agad, no? And with this assumption, with this polynomial equation, you get the displacement of the member, yan, which ultimately you will get the stiffness of the member. Yan. So parang dyan ko na nare-reconcile na natin dyan yung application ng curve fitting sa Lagrange polynomials in the way of Lagrange polynomials. Tapos on a larger sense, on a global sense, once you apply the Lagrange polynomials sa finite element, you will solve the system of equation using chapter 3. Ganun po. Next is numerical differentiation. Yan, alam naman po natin, no, sa calculus, may differential calculus. Yan. And then meron ding integral calculus. So to solve the derivatives, the numerically, so this is the approach, no? Finite difference, no? Finite difference formulas using Taylor series. Yan, madami po to, no? May central difference method. Yan. Sa amin, sa civil engineering, ang magandang application yan is yung structural dynamics, no? Okay. So, insert new page. For example, this one, meron kaming accelerogram, which is the graph of acceleration versus time. So, ganyan siya, no? Gulo-gulo, no? Yan. So, using numerical differentiation, we will we will assign an interval very very small, say every 0.1 seconds or even 0.05 something. Yan. And then if you zoom in this curve, para siyang ganyan. Bawa ganyan. Okay. Take note, acceleration versus time. Yan. Yan po. Yan. Tapos, remember, acceleration is the derivatives of what? Velocity. No? And velocity is the derivatives of the displacement. Yan po. So, using numerical differentiation, mababack calculate mo yung velocity going dun sa displacement. Parang ganun po, no? By assuming a very small amount of time. Yan. There's that. So, ganun din. May Lagrange polynomial ano din, no? Okay. Numerical partial differentiation. Okay. So, kung may differentiation, may integration. Yan po. So, rectangle and midpoint methods, trapezoidal method, Simpson's method, Gauss quadrature, yan. Richardson's extrapolation, Romberg integration. Again, so on a larger sense of application ng finite element analysis, ang gamit naman namin sa civil itong Gauss quadrature. Yan. Gauss quadrature kasi sorry, insert new page. Okay. So for example, this is a slab. Concrete slab, 'di ba? Tapos dinidiscretize namin 'yan, no? So we assume a mesh. Yan. Kaya nga finite element, no? Finite, no? Exact, 'di ba? May boundary, no? And it's an element. Yan, finite element. And then you analyze that finite element. No? Now, you ano diyan, no? You will get portion of that, no? And this plate, we call this now a plate element. No? This is now a plate element. Yan. We will assume a displacement function for this plate. No? Kumbaga, say if this plate displaces 1 unit, yan. Pause. Yan. So the other degrees of freedom, yung other coordinates niya will be 0. Yan. Then we will get the corresponding displacement function for that. So ganun din, so on so forth. Ganun din, mag-a-assume ka dito ng 1 unit displacement, another 1 unit displacement, tapos get the displacement function. Okay, parang ganun po, no? And once you have the displacement function, okay, ayan. So once you get the displacement function, you will now be able to get the B matrix. The displacement function is simply yung yan din yung ano, no, yung shape function matrix mo, no. Tapos pag na ano, essentially parang mag-differentiate mo lang yon, you will get the B matrix. Tapos the formula for stiffness is B transpose DB, wherein D is yung constitutive matrix, no? Depende na yan sa analysis mo kung plane stress, no? Yan, kung plane strain, yan po. Tapos yun po, no? So you will operate this matrices and then you will get the K using Gauss quadrature. Yan po. Kasi si Gauss quadrature, ang limit ng boundary mo is from -1 to 1. Yan. So, parang ano po to, parang this is integral, no? Integral from -1 to 1. Therefore, itong ating real life plate, no, wherein may coordinates yan, say 0.5 meters, no? Say 0.5, 0.5 by 0.5. Imamapping mo pa yan, no? Imamapping mo pa yan to a negative 1 to 1 region. Okay? So, parang pag tiningnan mo siya plan-wise, yan. So, meron kang 4, magkakaroon ka ng 4 points sa loob ng isang plate. Yan. Tapos, na in a coordinate, you call that the natural coordinate system from negative 1 to positive 1. Tapos, ganun din po. Yan. So, this is negative 1. Yan. Yan. Ito yung i-convert mo ngayon yung ang tawag namin dito is isoparametric element, no? I-convert mo yan into this real life structure into an equivalent element in a negative 1 to 1 natural coordinate system. Tapos using Gauss quadrature, operate that, you will get the stiffness. Parang ganun po, no? So dito sa atin mas yung hindi tayo sa finite element approach, no? Sa mga polynomial lang tayo. Yun lang yung maging application natin. Pero sinasabi ko na lang na yun nga, it has a direct application sa civil engineering. Actually, finite element is also for all engineering naman no? Yan. Meron din sa mechanical, no? Meron din sa electrical, yun po. And they're using Gauss quadrature din. Yan po. Okay. So at least by that lesson, ma-apply nyo yun going to the major subjects na you will take up later on. Okay, then proceed na ngayon tayo sa initial value problem na. Andiyan na yung mga Eulers, di ba? Modified Euler, Runge-Kutta methods. Yan. So, ito na yung mga first order differential equation. Yan. Ang ano ko dito, good example ko dito yung no? 'Di ba yung movie na na Hidden Figures. Yan, yung movie na Hidden Figures. Yan, okay. Parang inestimate nung scientists from NASA, kaya Hidden Figures sila kasi Black American sila no? Mga Black American scientists or mathematician, they estimated the projection ng rockets ng NASA, okay, by Euler method. Using Euler lang, no? Nung wala pang masyadong hindi pa mataas yung specs ng mga computer noon, no? Diba, alam naman natin, projectile is something like that, no? Sa Euler method, if you have the initial value, kaya nga initial value problem, you will estimate the path of your projectile, no? Using the assumed initial value. So sa initial value problem, meron kang initial value na given, tapos mag-a-assume ka ng slope of your equation. You have the initial value, you assume the slope, then you will come up with the next value. Ganun lang po, no? Basically ganun lang yung idea. Yan. So kung may initial value problem, may boundary value problem naman. Now, wherein sa boundary value problem is say ito, no? Say fixed beam. Yan. Yan. Fixed beam. So may boundary ka, no? You have the parameters on both ends, no? Say at A and B. So there sa A, the displacement at A is 0. The rotation at A is 0. The displacement at B is 0. The rotation at B is 0. So boundary value na yan, no? Tapos if you know the equation of the differential equation of this the elastic curve of that beam, no? Apply the boundary given, the values of the boundaries given, you will be able to solve the displacement of the system. Basically, ganun lang naman po yan, no? And yun nga rin, finite element is actually a boundary value problem. Diba? Naalala nyo yung slab kanina? is that you can only solve this system pag nag-set ka ng ano dito, ng what do you call that, ng boundary, no? Say at this location, fix ano siya, fix fix support. So therefore, yung mga nodes dyan, yung ng finite element mo, isi-set mo ng displacement ay 0 para ma-solve mo sila. So basically ganun po, no? Yan. Yun nga lang, dahil finite element, so diniscretize mo siya into many elements. So nagiging ano rin siya, nagiging system of linear equation na rin siya. Ayan, parang na-reconcile, no? Boundary value problem, na-reconcile with numerical integration, na na-reconcile din naman sa system of linear equation. So, yun yung beauty nitong numerical methods po. No? Okay, that's why na I chose din na magturo ng numerical methods kasi I was able to reconcile those ano no those concepts. Yan po. Okay, so that is basically yung overview po nung ating course.